Okay, can we start?
Yeah.
So, welcome everyone to, since we're broadcasting from Barcelona, I should say afternoon lectures of our summer school on qualitative theory of piecewise ordinary differential equations. It's a pleasure to me to introduce the next speaker, Thiago de Carvalho, who is a professor at Universidade de São Paulo, Brazil, and is an expert in Filipov system. His lecture is about structure stability and bifurcations of low codimension in piecewise differential systems. Thiago, please.
Thank you, Douglas. I would like to thank the organizers for the invitation. It's an honor for me. And I would like to say sorry about my English. It's not so good, but the presentation also is in English and you can follow by it. And well, we'll talk about structural stability and bifurcations of piecewise smooth vector fields. Well, the qualitative theory about ordinary differential equations is well developed, and recently the piecewise smooth vector fields are playing a very important role in the theory, principally in the applications where a kind of on-off key change the rule of the system. No? At this course, we will talk about qualitative theory of smooth vector fields. We will try to understand what is a piecewise smooth vector field following the Filipov rule. Okay, it's important. We will talk about the differences between smooth and piecewise smooth vector fields in R2 and R3 principally, and we will talk about structural stability of piecewise smooth vector fields and bifurcations. Well, let's start with smooth vector fields. When we have an equation like this, okay, we have a function f and a vector x. This function f is of class CR, okay, and we define with this a vector field x, capital X, okay. This vector field, as we know, have regular points and singular points. What is a regular point? A regular point is a point such that f is not equal to 0. A singular point is a point where f is equal to 0. We will see in this course that isolated singular points can be classified in some sense, and after this classification could be more difficult if this depending on the complexity of this 0 here. Well, the classification of smooth vector fields are based on a fact that all vector fields in a set can have or not the same topological type. But what is the this sentence, no? What is the same topological type? Okay. In order to answer this question, you need to define what is the same topological type. And this is done here. Two vector fields, two smooth vector fields, two CR vector fields, X and X tilde, defined in neighborhoods of the origin, are equivalent if there exists an orientation preserving homeomorphism that sends orbits of, let me do a picture here. So we have two neighborhoods of the origin, and there exists this homomorphism that sends orbits of X, two orbits of X tilde, okay? Moreover, if the homeomorphism preserves the parameterization by time, we will say that these vector fields are conjugated, okay? So when two vector fields are equivalent, when there exists this homomorphism, these vector fields have the same topological type. Moreover, if in a neighborhood of this vector field, all other vector fields are topological equivalent to it, no? To X, we will say that X is structurally stable, okay? So in this case, this point is the vector field X. There exists a neighborhood of X such that all vector fields here have the same topological type of X. In the classical theory about smooth vector fields, I believe that this is the first classification or a classification theorem, that is the flow box theorem. It says that if you have a vector field of a C1 vector field, okay, such that P is a regular point, P is a regular point. So let me make a picture here. So if P is a regular point, it's not a stationary point. Let me picture this in a different way. Here, P, okay? If P is a regular point, the flow box theorem says that it's possible to obtain a vector field Y. Moreover, this vector field Y is constant, okay? And X and Y are equivalent. So we have an homomorphism between R in a neighborhood of P and the constant vector field, okay? With this, we have a better view of what's happening around the point P, okay? This is the content of the flow box theorem. So, since we have understood everything that happened in a neighborhood of a regular point. Okay, we next we'll talk about singular points. So a singular point or an equilibrium point, as we said before, is a point such that it's a root of the function f. Okay. And this equilibrium point is a hyperbolic equilibrium. Okay. It will be an equilibrium of easy behavior. Let's say this. And so the equilibrium will be hyperbolic if the derivative of f have eigenvalues with distinctive of zero real parts. Okay. So the next theorem will say what is happening in a neighborhood of an equilibrium, a hyperbolic equilibrium point. This is the Grobman-Heightman theorem, again for C1 vector fields. Okay. So what says the Grobman-Heightman theorem? He says that if you have a hyperbolic equilibrium of x, okay, so there exists a homeomorphism H that conjugates, that makes an equivalence between x and the vector field x dot equal to df calculated at x0, the Jacobian matrix. Okay. There exists an homeomorphism between x and the linear part of x. And for example, if you have here I don't know, a saddle, a nonlinear saddle, and if this saddle is a hyperbolic equilibrium, so the Grobman-Heightman theorem says that there is a homeomorphism that provides an equivalence between this saddle and the linear one. No, so it's wrong. And the linear one. That's okay. Just like the flow box theorem, okay, this can be done in Rn. This is important here, because some of the next theorems that we will see, they cannot be applied to Rn. So with this Grobman-Heightman theorem, we understand, we can say what is happening with in a neighborhood of an equilibrium point. Okay, in a neighborhood of an equilibrium point, even the function f is not linear, or it's complicated, we can conjugate this vector field with a linear one, and in a linear one, we start the agent spaces and so, and we can and we are able to say what's happening in its neighborhood. The next slide says what is a limit cycle. A limit cycle is a global phenomenon that where we have a closed orbit that is isolated. Okay, so if this closed orbit is isolated, we call it a limit cycle. For example, it's not happening in a center. Okay, in a center, we have a lot of closed orbits, but they aren't isolated. A limit cycle, we are saying that this closed orbit is isolated. There is a neighborhood of it such that we have just this closed orbit in this neighborhood. Okay. Also, for a situation like this, we can, and I will not be more precise about this, okay? But we can a hyperplane that's transversal to this unit cycle, and at the intersection of the limit cycle and this transversal section T is the point P0. Okay, so we are able to define a first Heightman map. In the following way, we get a point P here, and so we see where this point, where the trajectory passing through this point will reach T again. Okay, so let me picture here. We have the point P0, the point P, and after a turn, the trajectory returns here. This point is the first return of the point P. Okay. I will let here another side. Prove that this function is well defined, okay, in this situation. And of course, the transversal section is defined in a more accurate way in the texts, in the literature. But this is the global vision of the first Heightman map. So a limit cycle will be called hyperbolic if the derivative of the first Heightman map at the point P0, okay, that is the intersection between the limit cycle and the transversal hyperplane. If this derivative is distinct of 1, okay. Moreover, I haven't written here, but if the derivative is modulus is smaller than 1.
Sorry, Tiago, I have a question. Just to be precise, you are using hyperplanes, then you are thinking in Rn, but if the derivative is 1, is because you are thinking in the plane. Is maybe.
Yes, I'm using hyperplane here. No. Yes, in Rn. This is true in Rn. For example, you can have a clear slide. If you have a closed orbit in Rn, so we can consider a hyperplane crossing in a transversal way this this limit cycle. Okay. This was your question.
My question is that when you think the derivative, you have a matrix, then you should talk about the eigenvalues of this derivative, no? Because you are in dimension Rn minus 1 in the derivative of the return map, not? You cannot say 1 or not 1. This is in the plane.
Okay, you are saying that it's a codimension 1 hyperplane.
Exactly.
Okay.
Doesn't matter because mainly we will work in the plane, but and then the derivative is 1. It doesn't matter. But in general, this is depends on the eigenvalues of this derivative matrix, no?
Yeah. Yeah. Here I will not talking about the maybe I could do it better, but I'm not being so how can I say so rigorous here about this situation, because in fact I would have to define what is a transversal section and the linear part concerning this. I'm just to give a global vision what is a first return map. But you are right. That's okay, John?
Okay, please continue. Thank you.
So if the derivative is smaller than 1, this limit cycle is an attractor, okay? Okay. Maybe to talk about this, it's important to give a two-dimensional picture. So if the derivative is smaller than 1, it means that the trajectory is approximation. The point is 0. And when it's bigger than 1, we have the opposite situation. Well, as before, when a limit cycle is hyperbolic, it's hyperbolic, all other vector field in a let me picture this. When the vector field x is hyperbolic, when the limit cycle of the vector field x is hyperbolic, all other vector field y in a neighborhood of x also has a limit cycle, and moreover, this limit cycle of y also is hyperbolic and behave, and they have the same behavior, behavior. If you one is attractor, the other is attractor too, and so on. So this vector field X is structural stable. Okay. Those vector fields have non-hyperbolic equilibria or non-hyperbolic limit cycles will be called structurally unstable. For example, if you have here a limit cycle that attracts the trajectories outside it, and repels the trajectories inside it, it's possible to perturb this vector field in such a way that we broke this connection here, for example, and this is the new situation where we broke this connection. Okay, let me see if it's okay. Okay. And so we can put here, we can draw this in this way, and we haven't here a limit cycle. Okay. So if the limit cycle is not hyperbolic, we can have this situation. There is a diagram that I can picture here. For example, let me see. No, I will not picture this. I will let you to make this after, because let's introduce the things first, okay? But the non-hyperbolic limit cycles or the non-hyperbolic equilibria can generate distinctive situations near a vector field X. Okay, this is the vector field X. This is the vector field X tilde in a neighborhood of X, but with a distinctive behavior. Another situation that is structurally unstable, okay, is when we have a separatrix connection. For example, if you have two saddles, okay, two saddles, here a saddle S1, here a saddle two, and in some sense we can glue these separatrices. Okay, so here we have a separatrix connection, and of course, if we impose a perturbation on this vector field X, we are able to obtain, well, first, the saddle one, if this is a hyperbolic saddle, it persists, okay? Well, we also have a hyperbolic saddle here. The saddle 2, if it's hyperbolic, we also have a hyperbolic saddle at the perturbated system, but this connection can be broken. So we can have a situation like this, and so these two behaviors are not equivalent. Why they are not equivalent? If we return to the definition of equivalence, we say that we can send a trajectory in a trajectory, but for example, the trajectory by this point is this, okay, and the trajectory by this point is this one. So the trajectory passing through P and Q and this point can be must be sent in this trajectory and in this trajectory, but these trajectories are distinct, okay? So there is not an homomorphism sending the single trajectory in a single trajectory, and so the vector fields are not equivalent. Let me see here. Here is what I explained before. Well, in order to continue, we need to define some sets here, some objectives. First of them, where is a omega limit set? So let x0 such that the flow, this is not the notation of the flow, okay? The flow of x by this point x0 is well defined for t positive. Then the omega limit set is the set of points, the set of points such that there is a sequence of times Tn converging to infinity, to plus infinity, okay? And when you consider the flow with this times, okay, applied in this times, this is in these specific times, we have a sequence of points converging to x, okay? So what's happening here? Here is the point x0, and this is the flow, okay? This is not the notation that I'm using here. And in some sense, there is a sequence Tn such that this sequence of points, phi, t2, this sequence of points, okay, converge to the point x. There's a neighborhood here such that there is infinitely many of these points at this neighborhood, more than infinitely many, no? All then bigger than a time t, and 0 will belong, will belong to this neighborhood. This is the omega limit set. The same happens for the alpha limit set. At the alpha limit set, we will consider that the trajectory is well defined for negative times, and here we will change the plus signal to the minus signal. Okay. So these are the omega and the alpha limit sets. With this, after this, with this and after this, we will define what is a non-wandering point. A non-wandering point is a point such that each one of its neighborhoods meets arbitrarily large interactions of itself. I will picture this next here. A non-wandering set is a set composed by non-wandering points. And it's important, do not confuse wandering points and non-trivial recurrent points. Okay, we have to distinguish these points. A non-trivial recurrent point is a point that is non-periodic, because this is related with the word non-trivial, okay, non-periodic, and belongs to the omega or alpha limit set of itself. Let me make a picture here. Okay. Let's consider the following situation. We have here at the plane, okay, we have a vector field with this phase portrait. Okay, there is a set of equilibrium points, and these equilibrium points are connected by regular trajectories. Okay, so let's understand these two points here. What is a non-wandering point and what is a recurrent point? A non-wandering point, let's see again here. A non-wandering point is a point such that each one of its neighborhoods meets arbitrarily large iterations of itself. And a recurrent point is a point that belongs to the omega or alpha limit set of itself. Let's see here. Let's take a point here, a point P, okay? A point P at this regular trajectory. If you consider a neighborhood of it, okay, arbitrarily large interactions of this neighborhood, since we can define here a return map, arbitrarily large iterations of itself will have an intersection with this neighborhood. Okay, so the point P is a non-wandering point. Okay, and let us see if P is a recurrent point. P is a recurrent point if it if it belongs to the omega or alpha limit set of itself. But let's look here. The omega limit set of P is this point. I don't know, R, I don't know. This point R1. Okay, this is the omega limit set of P. Okay, and the alpha limit set of P is this point R2. So P is not a recurrent point. Okay. Non-trivial. What is the trivial recurrent point? The trivial recurrent point is, for example, a closed orbit or an equilibrium. Okay. These two objects are composed by trivial recurrent points. So there is a difference here. This is the difference between non-wandering and recurrent points. So we are able to talk about the Peixoto's theorem that completely characterizes the structurally behavior, the structurally stable vector fields on a, this is important, compact two-dimensional manifold without boundary. This version that I put here talks about manifolds without boundary. So C1 vector field, okay, this manifold is structurally stable on M if and only if the number of critical points and cycles is finite, and each one of them is hyperbolic. Second thing, there are no trajectories connection. Okay, there are no trajectories connecting saddle points, and finally, the non-wandering set is composed by equilibrium. I'm using, oops. I'm using this notation, okay? The wandering set is composed by equilibria and the limit cycle only, okay? This means that, for example, this situation does not occur, okay? And of course, this cannot occur because here we have this a kind of separatrix connection, okay? We have a separatrix connection between the unstable separatrix of R2 with a stable separatrix of R1. This can be broken by a small perturbation of the system. Okay, this can be broken. So the non-wandering set is composed just by equilibria and limit cycle. Moreover, if M is an orientable manifold, the set of structurally stable vector fields is open and dense in the C1 topology. Okay, So this result characterize the structurally stable vector fields. This is important because if you with this hypothesis, this is important because if you consider anything that is not at these sets, a vector field presenting a non-hyperbolic limit cycle or a non-boundary point that is not a equilibrium, for example, this vector field is structurally unstable. And what happens if M has a boundary? Okay, this is not a big trouble because in this case we must add some pieces of the hypothesis concerning the tangent trajectories. For example, if this is the boundary of M, we cannot permit that trajectories of the vector fields have a double tangents here, because you can perturb this in such a way that just one of them persists. Or for example, we have to discard to avoid the situations where we have a connection between, not between two saddles like this, like before, okay, but a connection between a equilibrium point, a saddle, and a tangent point with the boundary. These objects must be avoided if we are looking for structurally stable vector fields. Okay, let me see if I will stop. Let me talk more 5 minutes, Douglas. Can I talk more for
Yes, sure.
5 minutes? So there's a challenge for you to the next talk. For manifolds with dimension bigger or equal to 3, you could provide this is a challenge. Provide a kind of Peixoto's theorem. This, I believe that it's not done in the literature. Okay, so you can extend this theorem. Another important result here is about the qualitative theory of smooth vector fields, the Poincaré-Benson theorem. Again, it's for R2 or two-dimensional manifold. Okay. We consider a C1 vector field, a compact set where we take a point P, okay, and we consider the positive semi-orbit passing through P. If this positive semi-orbit is contained in the compact set, so when X has a finite number of equilibria, okay, at the omega limit set of P, one of the next 3 possibilities happens, or the omega limit set has no equilibria, and so it's a periodic orbit, or the omega limit set has no regular points, and so the omega limit set is a single, this is important here, equilibrium, or the omega limit set has regular points and equilibrium, and then the omega limit set is what we call a graph. It's a set of orbits converging to one of these equilibrium, like I draw, like a picture here, okay? This is a graph. There is a set of equilibria and trajectories connecting them. This is the content of the Poincaré-Benson theorem. Again, you can think about it for dimension bigger than 3. And I would like to say that for bidimensional compact manifolds, if the flow is C2, and we allow that the omega limit set is the manifold itself, then we can extend a bit here this theorem, and we add here that the omega limit set is the torus. Okay, is the manifold M that must be a torus. Okay, this is the Danjois-Schwarz theorem. Okay, this is what I plan to talk at this first part, and we will have a break here. Okay, and we return in 5-10 minutes.
10 minutes.
10 minutes. Okay. Thank you.
Okay, thank you, Thiago. So I see you all in 10 minutes.
Okay. Recording in progress.
Yes. So welcome to everyone for this second part of this lecture. So Thiago, please, when you want.
Okay, thank you. So after a review about the qualitative theory of smooth vector fields, we will introduce the piecewise smooth vector fields. Okay, and after this, I will talk about if the previous results, the previous theorems, can be reached for piecewise smooth vector fields too. So, what is a piecewise smooth vector field? Well, Professor Henri Ponce already has talked about this today, but let's define here again. So we consider a neighborhood of the origin in Rn, okay, in Rn, and we consider a function H that has has 0 as a regular value. Okay, so this neighborhood of the origin can be separated in two regions. A region where the function h is positive, including 0, okay, including 0, and another region where the function h is negative, and including 0 here too. We will denote the set of all CR vector fields by this letter, no? And we will consider this Cartesian product where we have where we define, no, a new vector field that will be the z vector field, such that z is equal to x if the point belongs to the region sigma plus, and the vector field z is equal to y if the point belongs to the minus region. Okay. Note that at a 0 of the function 8, so we have the following picture here. The X space is partitioned into two regions with a common boundary. Okay, with a common boundary, and at this boundary, all vector fields are considered. Okay, so at this boundary we have a double definition. Okay, for z. For a while we have a double definition for z. This means that z is multi-valuated at these points where h is equal to 0. Okay, so we will consider this function that is the canonical A-mirror product, okay, between a vector field x and the gradient of 8. This new function is very, very important here because it will provide us the kind of contact between the trajectories of the vector fields with sigma. Okay, if this function is 0, if this function is 0, it means that the vector field, it means that the vector field x is tangent to sigma, because the gradient of 8 at this point has a the inner product between this vector and the vector x at this point p, okay, is 0. The angle is pi over 2. So let's see what can happen here. Generically, what happens here? Okay. Generically, the points of the manifold sigma are the following, or the points of sigma are in a crossing region. That means that both xh and yh okay? These functions here have the same signal. This means that, for example, the trajectory of y is approximation is converging to sigma, and the trajectory of x is departing from sigma. Okay, they point to the same direction. Because of this, these functions have the same signal. Okay, can I compute this? This is for example, the modulus of this times, no, sorry, the modulus of this times this gradient multiplied by the cosine of the angle between these vectors. Okay, so in a crossing region, both vector fields at this point points to the same sense when compared with the gradient vector. Okay, or they point in the same direction of the same sense of the gradient vector, or in the oppositive sense. So if here we have the gradient vector, the trajectories are doing something like this, but both of them are in a opposite direction when compared with this. Okay, this is a crossing region. A sliding region is a region where, well, the functions have a positive signal, okay, but there are two ways to be opposite here, no? Or this is negative and this is positive, or this is positive and this is negative. The first one we will call the sliding region, or sliding attractive, is a region where, again, I will picture here the gradient, where the vector field x is pointing in an opposite direction when compared with this, okay, and the vector field y is pointed at the same direction of this, okay. So this is the situation. This is the sliding or the sliding attractive. The other region is the escaping region, okay, or sliding repulsive. Some texts in the literature call it a sliding repulsive, but I will call escaping. Okay, is this situation where the x vector field points to the same direction of the gradient of 8, and the y vector field points at the opposite direction. Okay, this function, so it's very important here in order to determine the orientation of the vector fields. To calculate this, okay. So at the sliding and the escaping region, we will define a sliding vector field at the following way. So we have here sigma, okay, and this is a point P, and we have here a sliding, okay. So this is the XP, okay, because it is a sliding region. So the X vector field is pointing down, and the Y vector field is in this sense. So we can consider this straight line, okay, connecting these 2 points, the point these 2 points, okay, this is the point P1 and the point P2. And so we will consider the vector belonging to this region that is tangent to sigma, okay? That's tangent to sigma. This vector, at this situation where we are working with a sliding region, this vector is, let me see the notation, is the sliding vector, is the sliding vector, okay? Is the sliding vector that I call ZS, okay? And doing this for all points in the sliding region, we will have a sliding vector field. Analogously, we can define the escaping vector field, okay, defined at the escaping region, and in both cases, we will call it by the sliding vector field, okay, and we will denote it by Z sigma in both cases. That's okay. And during the computation, the sliding vector field is written by this expression. Okay, here we have this number times this vector field. Here again, we have this number times this vector field. And here we have 2 numbers. Of course, this expression is not provided by the tangent, by the points where these numbers are 0, okay? These numbers are 0. Another definition. This is a how can I say? We haven't a consensus about these definitions, but I will define it in this way, okay? The flow of the vector field Z, okay, denoted by this, is obtained by the concatenation of the flows of X, Y, and Z sigma. Okay, how can I produce this concatenation? At the any way you are able to do. For example, let me make a picture again here. For example, if you are in this situation, okay, we have a quadratic contact here. What is the trajectory by this point? For positive time, the trajectory will follow this path, okay? For positive time, we will go to this path. Here we have a crossing region, and this is the only possibility to follow for positive time, departing from here, okay? But for negative time, we have a lot of choices here. For negative time, the trajectory can be this, or can be this one, okay? Can be this one for negative time, can be this one, can be this, or even can be a trajectory living here at the sliding region, okay? So for negative time, there is a lot of possibilities, but at the end, this is important. Once a time you choose one of them, this is the possibility that you choose, okay? You have, what I mean with this? Well, there is this trajectory, there is this other trajectory, and for example, there is this other trajectory, okay? Representing each one of the situations that I explained before. This is one trajectory, this is another one, and this is another one. Once you choose one of them, this is done. There is, so what's happening here? What's happening here is that there isn't the uniqueness of trajectories by this point, okay? There are a lot of trajectories passing through this single point, which is a regular point, okay? No, sorry, it's not a regular point. It's not an equilibrium point. It's not an equilibrium point. Well, this is what I call a concatenation. So we say that a point of sigma belonging to sigma is a sigma regular point if it's a crossing point, okay? Crossing point where both vector fields points to the same direction when compared with the gradient, okay? For example, here, points here are sigma regular, or when this point is not a regular a crossing point, it's a sliding or an escaping point, but it's not a equilibrium of the sliding vector field, okay? It's a sliding or an escaping point, but it's not an equilibrium of the sliding vector field, because you can have equilibria of sliding vector fields. For example, when we have a situation like this. Okay. When no. When you have a situation, let me reverse the orientation. When we have a situation like this, yes. So what's happening here? Here we have a crossing region, okay? And here I have a crossing region. At the middle, between these 2 points, there is an escaping region. There is an escaping region. Moreover, the trajectories near this point will follow the orientation of the sliding vector field near this point is this one. It's fallen from the left to the right, okay, near here, near this point. And near this another point, since we have a tangents here pointing to the left, the sliding trajectory will follow the direction of the tangent trajectory. So the sliding vector field is pointing to the right near this point, and to the left near this point. So for continuity, there is at least one equilibrium of the sliding vector field here, okay? So it's possible that the sliding vector field presents equilibria too. But the equilibria will not be regular points, a regular point of sigma. So we say that P is a regular point, not a singular regular point, but just a regular point of Z, if it's a regular point of belonging to a sigma regular point, okay, just like we define here, or it's a regular point of X or of Y, okay? These are the regular points of Z. Z is the piecewise move vector field. The points of sigma, which are not sigma regular, will be called sigma singular. And there are two subsets of sigma singular points. Those ones are the trajectory is tangent to sigma, okay, and those ones where the sliding vector field has a zero, okay, and this will be called pseudo equilibrium, okay, when the sliding vector field is zero, has an equilibrium, we call this pseudo equilibrium. The other set, sigma t, is the tangential set. This means that all points in this set are points where at least one of the vector fields are tangent to sigma, okay? Well, we will classify a bit more the tangent set. When a trajectory, the trajectory of X has a quadratic contact with sigma at P, we will say that P is a fold point, okay? It's a fold point. And this fold point, the contact is quadratic, And if the trajectory is at the same side, belongs to the same side where x is defined, this fold point is visible. Otherwise, for example, let me see here. For example, x is defined here, okay, at this up region, and it's possible that the trajectory of x tangent to sigma is this one, okay? This is a trajectory of x. So we can't see the trajectory of x because here at this region we define the vector field y. So we have here an invisible fold point, okay? This algebraically, this can be seen with the signal of the second derivative of the function it's the second, okay, it's not the second derivative of that function, but this function that I defined before also is called the Lie derivative, okay? And this one. And this one is the second Lie derivative. Okay? And with this, we can calculate the derivative. Okay, now there are some generic singularities of a piecewise smooth vector field defined in R2. Okay, which are the following. They are the hyperbolic singularities of x or of y, okay, defined at these open regions, and a generic singularity of z can also be a fold regular point. What is a fold regular point? Is a point where one of the vector fields has a fold point and the other one is transversal, okay? This is a fold regular point. Or a hyperbolic pseudo-equilibria of the sliding vector field. Well, the sliding vector field has an expression, and we can calculate his Jacobian matrix, okay, and see if the eigenvalues have a null or non-null real parts. Okay, these are the generic singularities. Another name that appears in the literature is this virtual or even real equilibria. So, for example, if we have here again the vector field x and the manifold sigma, it's possible that x has an equilibrium placed at the region sigma minus, okay? For example, here you have a 7. And so this will be called a virtual equilibrium of X. Otherwise, if the equilibrium is placed at the same region where X is defined, it will be called real. Okay. Note that, just to keep the notation, here we have a visible fault. Okay, a visible contact if the contact is quadratic, and here we have an invisible one. Okay, because the trajectory tangent, the X trajectory tangent to this point remains invisible here. Okay. Let's go. The first return map. The first return map in this context will be a bit different than the previous one. Let me see what. For example, when we have an invisible fold point for both X and Y, okay, we have here an invisible fold point for X and Y. The implicit function theorem ensures that given a point P in a neighborhood of the origin, okay, let's call this point P, there exists a smallest time such that the X trajectory passing through P will reach sigma again, okay? And this is we will expand a time here at this trajectory, and we will meet this point, okay? Let's call it P1. And this will be called the half return map. The half return map. Sorry about the dog. And this will be called the half return map. Okay. Analogously, we can define, given another points here. Okay, we can define the same for the vector field Y. The composition of these half returns, sorry, just a minute. So the composition of these half return maps will give us the first return map. So we depart from a point P and return again to sigma using X and after Y in a point P2. Okay, P2 is the first return of P, but we need to consider this composition. Okay, when we and there is a, let me see. Okay, and there is another way to define the first return map. We can consider the vector Y first. Okay, we can consider the vector field Y first, and after the vector field X. but it's the same, okay? Okay, so I believe that I will not finish this section today, but let's start it. Let's talk about smooth versus piecewise smooth vector fields. This means that we will looking for the difference and between these sets of vector fields. Okay, the first and the biggest one, the really biggest difference between smooth and piecewise smooth vector fields governed by is the Filipov's rule. Okay, this is important. That are the rules that we are considering here. Is the fact that the last one is for the last one there is not uniqueness of trajectories passing through a given point, as I said before. Okay, and this is really a difference here, and this will give a lot of consequences. But even with this non-uniqueness, some classical results have an analogous to the piecewise smooth context. For example, a version of the Peixoto's theorem was obtained by Jorge Sotomayor and Ana Lúcia Machado. It's here at this paper. I will talk about this paper tomorrow, okay? When I will talk about the structural stability of piecewise smooth vector fields. But just to know, there's a version of the Peixoto's theorem at this context. Also, there is a version of the Poincaré-Bengtson theorem for this context. Okay, it is published at here, and by coincidence or not, okay, both of them are published in journals of the universe that is giving this conference. Okay, this journal and this one are journals of the autonomous. Very well. And some classical results have not a piecewise smooth version. For example, and this is a challenge here, and you can expand the time here. Okay, it will be important for the literature. It's important to produce a Grobman-Heightman theorem in the context of piecewise smooth vector fields. Okay, it's very difficult because what is happening in sigma, at sigma, okay, over sigma. For R2, it's happening one kind of things. For R3, other kind of things. And okay, the Grobman-Heightman theorem is a theorem for Rn, and it talks about the Jacobian matrix, no? So how can we produce a Grobman-Hartman theorem for the context of piecewise smooth vector fields, general piecewise smooth vector fields? Okay. Again, you can think about this until tomorrow. It's okay. And the known uniqueness of the trajectories generates phenomena non observed in the classical literature. For example, a first course in qualitative theory of smooth vector field prove that you can see this in any of these courses, okay? When it's compact, the omega limit set of a trajectory is connected, but it's not happens here for piecewise smooth vector fields. For example, if you have a escaping region, okay? A escaping region, and this is a point P. What is the omega limit set of P? I don't know. It can be, for example, focus here, okay? There is a sequence of times such that the flow and one choice of trajectories departing from P, that this trajectory will convert to this focus, okay? Also can be another trajectory departing from P that converges to a limit cycle, and even can be another trajectory converging to a pseudo equilibrium and other things too, okay? So this set here, okay, of limit cycles, of omega omega limit points, okay, this one, and this one. The set is not connected. Also, there are results that establish that chaotic behavior can be observed even in planar piecewise smooth vector fields. Okay, for example, here, this fact is not observed by smooth vector fields, where chaos is not observed for planar smooth fields. Also, there are piecewise smooth vector fields defined in the sphere. Okay, the sphere, this two-dimensional manifold without equilibria. Without equilibria, this is not possible also for the smooth case. Okay, and among others. Okay, there are a lot of results in this sense, comparing piecewise smooth and smooth vector fields. A lot of them are challenges really difficult, okay, that we can think about and produce great results about this. Well, Douglas, it's okay. I will talk more tomorrow. Thank you.
Okay, thank you very much, Thiago. Any questions, comments? Okay, so if not, now we have a break, right? And we come back in half an hour.
With your talk.
Yeah, possibly. I think that's 5:30 in Spain time zone and 12:30 in Brazil time zone. Okay, so thank you very much. Ciao again, and see you all in half an hour.
Okay, bye-bye.
Bye-bye. Thank you.